Okay, we are at section uh, 15.4, comparing simple harmonic motion with uniform circular motion. And before I get into the PowerPoint lecture, I'm going to share uh, another Walter Fent uh, animation. And let's just get it started. And you can see that it's an object going around in a circle. But you can let's look at the Y component of the oscillation. You can see it just goes up and down. Almost looks like uh, the position of a block on a spring pendulum going up and down. Or if you look at the X component, it looks like the block on a spring going back and forth that they always show you um, in the textbook example. So you can see that both of these are simple harmonic motion, but look at how they translate into the circular motion of the unit circle shown on here. And we can see, you can look at this as this is their position vector. The red is the position vector. We can look at the velocity vector. We can see that uh, the velocity changes back and forth. But you can see that the uh, tangential velocity is uniform, and it's always tangent to the circle. Let's look at the acceleration. No surprise there. You have a uh, vertical acceleration, you have a horizontal acceleration, but look at um, the total acceleration, the sum of the two, and it's always inward. It's the centripetal acceleration. And of course, if we look, since there's a centripetal acceleration, there's a centripetal force on the particle. The center-seeking force always makes it point inward. So this is just, uh, especially if we go to the position, the red position vectors, you can see how the up and down simple harmonic motion or side-by-side simple harmonic motion gets translated to circular motion. And that's what uh, this section is about. Let's stop share there and go to the PowerPoint. Uh, and so, well, I may have jumped the gun here on the PowerPoint. Okay, I actually remember seeing one of these sewing machines. This is a sewing machine. It says Singer, and this was at my grandmother's house. I wonder whatever happened to that old sewing machine. It'd probably be worth something nowadays. But you would just pedal uh, this little foot pedal, and it would rotate this ring. Let's read the boxes. The back edge of the treadle goes up and down as one's feet rock the treadle. The oscillation of the treadle causes circular motion of the drive wheel, eventually resulting in additional up and down motion of the sewing needle. So your foot pedal makes a circular motion, which turns another circle and makes the needle go up and down. You can think of other examples. You can think of if you've ever seen a steam locomotive uh, train start up, you see there's a piston going back and forth, and it's translating from that back and forth motion into a circular motion of the train wheels. And so the example they use is a little, if you can imagine, a little ball on a turntable, and they're casting a shadow from a lamp onto a screen. As the ball rotates like a particle in uniform circular motion, the ball's shadow moves like a particle in simple harmonic motion. Um, okay, let's look at this. There's 4 drawings here, and you can see the first one. Uh, it's just the particle going around, and then they're showing its position, and the next one is showing the velocity, and the last one is showing the acceleration. Of course, we see the purple there is the centripetal acceleration. We see the tangential velocity, and we see the position. I'm going backwards now from D to A. So the particle is at point P at t equals 0. At a later time, t, the x-coordinate of points P and Q, are equal and are given by equation 1523. X sub t is equal to A cosine omega t plus phi. Excuse me. So you can see that P and Q, their x component is exactly the same. The x component of the velocity of P, the velocity of P equals the velocity of Q. And the x component of the acceleration of P equals the acceleration of Q. So the x component of velocity is minus omega A sine omega t plus phi. Where do we get that? Well, just do dx dt. Take the first derivative of position. You get minus omega A sine omega t plus phi. And that's what they did. The dx dt, you get minus omega A sine omega t plus phi. Now let's look. The ball in the figure moves in a circle of radius 0.5 meters. At t equals 0, the ball is located on the left side of the turntable, exactly opposite the position in the figure, because in the figure it's on the right side. What are the correct values for the amplitude and phase constant relative to an x-axis to the right of the simple harmonic motion of the shadow? Well, the amplitude is going to be the max radius, which is 0.5. So only A and C are eligible there. But if at t0 the ball is located on the left side of the turntable, opposite the position in the figure, then there's already it's a half a rotation difference. So the phase angle is pi. So it's 0.5 meters and pi. All right, and that's it for the simple harmonic motion. I will give you a link to the Walter Fenton. You can play with it and watch it.